Hello, honors physics students. All right, let's turn our problem set to problem 25 here. We're making a big deal about making sure that we don't just assume that all positive charges are protons and all negative charges are electrons. And here I find that we have a typo. Okay, so in problem 25, we're referring to this 13 microcoulomb charge, clearly not a proton, and yet in parts A and B it does say proton. So if you please just change the word proton to charge in both parts A and B. Okay. All right, so we're going to read the problem, and then we're going to draw it out, and then we're going to go to solve. Alright, so we got two plates, so off to the side I want you to draw those plates, and we know that the negative plate is always going to be the low potential, so we'll label it 0 volts, and the high potential is going to be the 5 volts, and I'll go ahead and draw the field between them, and then I want you to go ahead and solve parts A and B. Okay, so hopefully, of course, you drew the field pointing to the left. We're looking at a positive charge, and the question is, does the charge want to be at the positive plates? Well, it's a positive charge. Of course it doesn't. So when we're moving it from negative to positive, does it take effort, or are you holding it back? Well, that's going to take some effort, right? It doesn't want to be there. We have to push it there. That's taking the cooler food and moving it up the mountain. It takes a lot of effort to get it up the mountain, right? Because it doesn't necessarily want to be there. It's got a lot of potential energy there. Okay, so letter B asks for how much work is being done by you. And here I've underlined it, although I didn't have to do that. Just make sure that anytime you're talking about work done, you know if it's being work done by some external force or it's work done by the field. Maybe you want to underline it yourself or highlight it somehow. Alright, so if it's the work done by you, I'm telling you right now the answer is 6.5 to the 10 negative fifth joules. If you didn't get that, maybe you want to try the problem again. Specifically, if you got the right number but the wrong sign, you definitely want to try the problem again. Okay, so if you tried f delta x cosine theta, well, that's just not going to work, right? Because we don't have the delta x. You can't do f delta x cosine theta. So that's out, right? So what do we have to do? We have to think about this in terms of the change in potential energy, right? When you drag the cooler food to the top of the mountain, you are changing its gravitational potential energy. So same deal here. When you are moving this positive charge, you're changing the potential energy in the system, and that's going to be q delta v, not negative q delta v. And this is where it really matters. This is work done by you. If instead you said w equals negative q delta v, that's wrong. That's the work done by the field. And all those details matter because you're going to get the wrong answer. I mean, just think about it. If it requires effort to move this charge there, then we should expect a positive value. If instead you're telling me it takes effort to do it and you're doing negative work, then you're getting it wrong, and also you're not understanding. You're really not understanding what it means to be doing positive or negative work. But it comes down to just having the right signs. And so we just put the numbers in. It's VF minus V naught, and clearly it starts at the low potential, starts at 0, ends at 5 volts, so it's final minus initial. It's got to be in that order, right? Just like all the way back in the beginning of the year, we never have a choice in the matter. A delta is always final minus initial, and you just have to read the problem carefully. So you know, it starts at the negative, that's the initial, it ends at the positive, that's the final. Put your numbers in, you should have no problem getting the positive 6.5 times 10 negative fifth joules. All right, same deal here for problem 26. We have another pair of oppositely charged parallel plates. I'd like you to draw them this way. Draw the field, label the plates as 0 volts or 9 volts, and then do the whole problem and come back to see how I do it. Okay, so in this case the field is pointing upwards from positive to negative, and of course the negative plate is always the lowest potential, so we're going to label that 0 volts. The high potential is the 9 volts, that's going to be the positive plate. Okay, and we're moving a negative charge. It's starting against the positive and moves to the negative. Okay, so it starts at the positive and it moves to the negative. So what's our negative charge in our analogy? That's the helium balloon. Where are we moving it? We're moving it from the top of the mountain to the bottom of the mountain. So think about that. Imagine taking a helium balloon and pushing it down. Does that require effort, or are you holding it back? Well, that takes effort, right? You've got to shove that helium balloon down. This negative charge does not want to be near the negative side of this system, right? And that's one of the reasons why I specifically want you to keep drawing the plates differently, so we're not always visualizing it the same way as height, right? This sort of plays with your mind a little bit. You're saying, oh, the negative charge wants to go up, so it wants to be there, but that's not up. We have to differentiate between up in the, actually height and the change of potential. This is the bottom of the mountain. That's the low potential, and that's where the negative charges are. It does not want to be there. It's going to require effort to move it there. All right, should the field be doing positive or negative work? Let's think about this. The field is pointing up. This is a negative charge. Which way does it feel an electrostatic force from the field? Well, it feels a force down, of course, right, against the field or towards the positive plate. So we're moving it up. The field force is pointing down. Is that positive or negative work? That's negative work. There's an angle of 180 degrees between them. The field is doing negative work. Remember, if we're talking about the field, you have to look for the force of the field, not the force you're using. Because we're not asked about that. It's asked about the field. So you have to look at the force in the field, and that's the force that's against this field that's going to point this way. And it's moving the opposite direction. That's negative work done by the field. Okay, which is initial, which is final? I mean, it's just a matter of reading. It starts at the 9 volts, ends at the 0 volts. Want to find the work done? I'll tell you the answer here is negative 0.0648 joules. And once again, if you got the wrong answer, try it again. Specifically, if you have the wrong sign, you really got to start attacking that. If this is now the second or third time you're getting the wrong sign, something's going wrong, and you're not understanding. You've got to go back and review all this stuff. All right, so in this case, it's going to be the work done by the field, because that's what it says. It says work done by the field. In this case, it is W sub E. In this case, the negative sign is in the equation. If you're missing any of those details, I'm not sure why you're missing those details. We're so detail-oriented in this course, and since the beginning of the year I've been telling you about that, right? You can't miss that stuff. Don't allow yourself to miss that stuff. Don't allow yourself to miss the fact this is millicoulombs, right? That's not micro. This is milli. That's 10 to the negative third. All those details matter. The initial is the 9 volts, the final is the 0. So in this case, we have a negative sign in the equation, a negative sign in the charge, because remember there's no absolute value, and a negative sign from the 0 minus 9. All that amounts to a negative sign here. Now, if you happen to get this answer correct, but you missed some of these negative signs along the way and just did it by coincidence, you really go back and figure out where you're making these mistakes, and you have to get these mistakes out of it, right? You have to get these things right. All the details matter. Let's go on to problem 31 and 34. So here, try it on your own. Come back, I'll talk through some of the details, but a lot of this is very straightforward stuff. Alright, 31, we're just doing an application of our shortcut equation. We should be getting delta V equals 120 volts. We have the field strength. We have the delta D here, how far apart they are. We're just taking absolute value of everything, so it's a potential difference of 120 volts. Something to note here, though, is about the units. So let's just go away from just the calculations here. Let's talk about the units for a second. When we do E delta D, the electric field is in newtons per coulomb, and the delta D is in meters. So it's newtons times meters over coulombs. And hopefully remember, a newton meter, that's the same thing as a joule. So joules per coulombs, that's how we defined a volt, and that's how we're getting volts here. Now, in the end, if you left your answer as newton meters per coulomb, there's nothing technically wrong with that. Even if you left it as joules per coulomb, nothing wrong with that either, but it's really good to see how all the units combine to get back to what we expected. The potential difference should be in volts, and here you see the units combining to get a units of volts as your answer. So that's all good. Alright, for problem 34, you have all the answers, and if you haven't already done so, please pause the video and try them all on your own, because you have all the answers. You should know if you're getting them right. Alright, really nothing much I want to talk about here because you're either getting it or you're not. You know, there's obviously a conservation energy sort of approach here. Notice that the low potential is not at 0 volts, it's at 120 volts, and so the delta V is not just 410 minus 0 or 0 minus 410. You have to account for the fact that it's at 120 volts, and that's possible. The lowest potential does not always have to be 0, so here I'm challenging that aspect of the problem-solving technique. Something I do want to notice here, right here at the end here for letter E, is our units of electric field strength. Normally our electric field strength is measured in newtons per coulomb, right? But when you do E equals delta V over delta D, which I hope is the equation you use to do this, the units should be volts per meter because the potential difference is in volts and delta D is in meters, and so we should be getting units of volts per meter. It's not really right to write newtons per coulomb because that's not what you're doing. We really should be writing volts per meter because that's what you've been doing, although you can see right up here that if we just divide both sides by meters, this is newtons per coulomb, put the meters over there, clearly we're showing that a newton per coulomb is the exact same thing as a volt per meter. So they are interchangeable. So in that case, it's not wrong, but I'd say it's better to write volts per meter because that's really what you're doing. And so you just want to get used to the idea that you will start to see some electric field strengths given in volts per meter instead of newtons per coulomb, and just recognize they are equivalent to each other. Okay, let's finish up here with problem 35. Again, read the problem, do it on your own, come back. Okay, so here the plates are not labeled with their potential, but we know that the lowest potential is always going to be at the negative plate, the high potential is the positive plate, so it's going to be 0 volts at the negative, 84 volts at the positive. Great. Here we're given different positions along the way, and we're going to find the potential each letter position. A couple different ways to do this. There's the long way and the shortcut way. I'm actually going to go with the long way first to validate that way of doing it, because you do delta V equals E delta D, and rearrange there to find the field strength. That's going to be 700 volts per meter. Notice here I'm using volts per meter, not newtons per coulomb, although it's not really wrong to use newtons per coulomb. It's not exactly right either, because yes, they're interchangeable, but we're doing potential over a distance. We should be using volts per meter as our field strength units. And then just put it right back in to delta V equals E delta D to find the potential from 0 to A, from 0 to B, from 0 to C. But if you're a little more savvy about it, you should recognize that this here is a linear equation, right? That delta V equals E delta D means that with it being a uniform field, every different delta D is going to have the same relative delta V. And so you should say, wait a second, if there's 12 centimeters between them, Well, letter B is halfway, right? So it's going to be halfway. You should just get halfway between 0 and 84. Letter A is 1 centimeter out of the 12. It's just going to be 1/12 of the way. 11, well, that's 11/12 of the way. And so if you did it just by proportions, that's not wrong. In the end, we should be getting 7 volts here. That's 1/12 of 84. 42 here, it's half of 84. 77 here, that's 11/12 of 84. And so either way is completely valid. All right, for letter C, I want to find the force at each different location to put a proton at A, B, or C. So I'm just going to set this up here. Find the force at A, find the force at B, find the force at C. Can we do Coulomb's law? Ooh, can we do K, big Q, little q over R squared? No. Well, big clue is I didn't actually give you the charges on the plates. But even if I had, we still know we can't do that. So it's always important to know when we can do the equations and when we can't. Remember, Coulomb's law is only for point charges. All the charges in the equation have to be point charges. And yes, we're moving a proton. That's clearly a point charge, but these plates are not point charges, which means Coulomb's law is invalid. So what do? Well, we just do Fe equals QE, right? The electric field equation rearranged for electrostatic force. We have the field strength, which we just found before. So if you had done the shortcut of just doing the proportions, at some point you had to find the field strength at 700 volts per meter, put it back in, and we should be getting 1.1 times 10 - 16 newtons up, because hey, it asked for magnitude and direction. I wonder, did you only find the magnitude and skip the direction? I'm not sure why you're doing that. It is April. We should know. If it says direction, you should give a direction. How do we know the direction? Well, it's all about rule 1. Right? You put a positive charge in here, and yes, we haven't actually drawn it, but we know the field lines are going to point upwards towards the negative plate, and so the field will apply a force upwards on a proton. But that's only at letter A. What about letter B or C? Did I get you? I hope I didn't. Wait a second. These oppositely charged parallel plates, it's a uniform field. That's the beauty of oppositely charged parallel plates. This field's going to be 700 volts per meter here, 700 volts per meter here, 700 volts per meter here. And so the idea is if there's a uniform field, the force is the same everywhere. If the field is the same everywhere, the force is the same everywhere. So you should not have recalculated. I hope you didn't, because that's really a complete waste of your time.